Hello and a very warm welcome to everyone who has joined us today. My name is John Norman. I'm Head of Marketing at Optimisation and moderator for today's webinar, which is perfecting the use of imperfect QSAR models, in which we will examine the effective use of QSAR modeling in drug discovery and discuss a variety of pain points for medicinal chemists in knowing when a model can be trusted and how to avoid common pitfalls. Peter and Matt will be discussing key learning points for the successful use of QSAR models and how they can be used to make better decisions in a multi-parameter optimization workflow to select and design high-quality compounds for your projects. So let's get things underway, and I'll pass the baton over to our presenters, who once again are Matt Siegel and Peter Hunt.
Thank you very much, John. Thanks for your kind introduction, and thanks to everyone for joining us today. It's so good to see so many people there in the audience, all over the world from what I can see, from the United States, Europe, and Asia. So Peter, before we get started in earnest, I wondered if maybe you could give us just a little bit of background on QSAR modeling and its applications.
Certainly, Matt. Thank you very much. Yes, it's actually quite a pleasure for me, as old as I am, to actually talk about something in computational chemistry that's older than I am. And it was Hansch and Fujita's work back in the early 60s that really kick-started QSAR as we know it. And yet there are still questions that we receive today which show that really the understanding of QSAR and what it can do for people really isn't embedded in the community.
Yeah, absolutely. I mean, we hear lots of questions about QSAR models when we're talking with the users of our software, but also scientists in general. And so I think what we thought we could do today is discuss some of the questions that we hear very frequently, and hopefully give some insights to help the community and to help you to use QSAR models effectively in the course of your drug discovery projects.
And it's not really just drug discovery projects, Matt, as well. It's the fact that QSAR models now are key in the increasing interest in generative chemistry. We don't rely on purely medicinal chemists thinking up structures. We're now putting that task more into the hands of a computer and having it try and evaluate whether those compounds are worth making or not. So QSAR models and their application is becoming even more vital to go through many more compounds than we can ever think of. So really for today, what we want to do is go through a number of things that we've been asked by the community, and hopefully it will help. But first things first, really, I think we should get a few definitions. So what do we mean by a QSAR model? Matt?
Thanks, Peter. So yes, what is a QSAR model? Well, at its heart, a QSAR model is basically a mathematical function, shown here as a function f, that takes as input a set of characteristics of a compound structure. Here are the x's, and from that generates a prediction of a value for a particular property or activity of interest, y here in this equation. So to give a little bit more detail, of course, we have to start with some data. That defines what y is for a number of compounds. We need the structures and their experimentally measured values of the property or activity of interest. Now, when building a model, the quality of the data that we use is absolutely essential. If we put in noisy or junk data, then we're just going to get a poor model, no matter how good the underlying mathematics is. And one thing that's been observed many times is that if we're going to use publicly available data from a database like Chembl or PubChem, this needs very careful curation. And indeed, in many cases, just simply may not be good enough to build a model. The second thing we need are descriptors or characteristics of the structure of a compound. Here in the equation are x's, and these can take a range of different approaches. They could be whole molecule properties, things like log P, lipophilicity, molecular weight, polar surface area, charge, flexibility, but also structural descriptors that capture key functionalities and their relationships, commonly denoted by the smarts line notation, or maybe by fingerprints and so on. So for any compound, we can calculate these x's as input to our function. And then what we need is some statistical fitting or machine learning method that will fit the form of this function between those descriptors and the observed values for our property of interest. And again, there are numerous approaches taken for this, from simple things like multiple linear regression or partial least squares for building linear models, but also more advanced sort of machine learning methods. Things like deep neural networks are very en vogue now, support vector machines, random forest Gaussian processes, and the list is almost endless. And of course, one thing we also need to be aware of is that no model is perfect. And so in addition to a value that's predicted by a QSAR model, there is also statistical uncertainty. In some cases, as we'll talk about later on, very significant statistical uncertainty in those values.
One of the questions that we have asked is really, how can we assess the QSAR models that we've got? And indeed, how good is your model compared to ours? And so what I wanted to do was just describe how we believe the best practice for generating a QSAR. You'll have a data set, and that whole data set needs to be split into a number of sections. A set of that data is there to train the models, and then a set of that data is there to test. Now, because in StarDrop, the automodeler, we have the ability of providing quite a number of different statistical techniques, we need to be able to decide which of those techniques has provided a good model. And so in our splitting techniques, we have two test sets in essence. We have a validation set and a test set. And it's the validation set which is there to test all of the methods and the models produced by those to see which method has good performance. And then once we've used that validation set to make our decision as to which one of these methods has produced the best model, then we test it again, because really we could, in this splitting process, have fallen prey to random chance. It could just be that the model that we've picked in the validation set is good by chance, and therefore this independent test again of that best model is something where we can assess whether that model performs equally well on an independent set which it hasn't seen. These sets can be created automatically or manually, depending upon how you want to test and create your model. But having found your best model, you need to understand really just how good it is. Matt, some statistics.
Indeed, ultimately we start to look at the statistics of the models to really assess the quality and how reliable those models are. Our particular choice when we're looking at a regression model, a model that predicts a numerical value, is the so-called coefficient of determination. We choose this because it's a measure of the fit to the identity line y equals x. So in a plot of observed values versus the predicted values, a perfect model, all of the predictions would lie along this blue identity line, the line of perfect fit. So we use this coefficient of determination. A value of 1 would indicate that perfect model. A value of 0 would be equivalent to random numbers, so not very good at all. And in fact, you can even have a negative value of the coefficient of determination, which indicates you're doing worse than random and really indicates a very poor model indeed. One source of confusion, though, is that there are different R-squareds that are often talked about. So the coefficient of determination here is shown as sort of capital R squared. This is not actually the same as the squared correlation coefficient. Again, another version of R squared. And this is actually a measure of the fit to the best fit line. So this is shown in this particular example by the orange line here. You can see that the best fit line isn't necessarily the identity line. And so here you can see that the squared correlation coefficient is 0.86, and that's higher than the coefficient of determination in this particular case, because this best fit line is not y equals x. So it's always important to consider, certainly when you're looking at different types of models and different publications and so on, exactly what statistic is being used to compare between different models. Another common statistic we look at is the root mean square error, or RMSE, and this is basically a measure of the average error in prediction as well. So in this particular case, a small value is good because the model on average is producing smaller errors in its predictions. So statistics are important, but they aren't the be all and end all. It's also important to look a little bit beyond the statistics. Peter.
Indeed so, and this is my particular favorite illustration of why statistics aren't necessarily the be all and end all. Anscombe's quartet. What we show on the right hand side is that he produced 4 data sets of exactly the same number of points. They have all of the same summary statistics, mean X, Y, variance, correlation, etc. But you need to plot them out here in these 2, X versus Y. On the top left-hand side here, this is a standard plot that everyone seems to see. We have a nice linear regression line. There seems to be a trend there that Y is related to X. But on the top right, yes, we have Y related to X, but it certainly doesn't look to be linear. So having a representation of this data as a linear model is probably missing something. The bottom left here, again, Y is related to X in a nice linear fashion, so it seems, but in this particular case, the linear model that we've got isn't quite right. It's being biased by an outlier. And really, why have we got that outlier? It's prompting you to look at the data that you have and see why you might be getting these particular outlying points. And then finally, on the right-hand side here, it's a very common occurrence. And instead of having 11 points and a line between them, in truth, you have 2 points. You have a mélange of points with a low value, and really the model isn't able to distinguish the actual values of these. It just knows that they're going to be low, and it's completely biased by a single point at the top right. And this is an occasion when, in fact, in reality, you may have a data set where you have a poor distribution of activities. You've got low active compounds and high active compounds, and it just so happens that those low compounds come from one particular chemotype and the high compounds come from a different chemotype. And in fact, what your model does is it differentiates chemotypes. It doesn't differentiate activities. And so having this situation where you have a cluster of points gives you a wonderful linear relationship, but it's not really relating the features to activity. One other data set which I have recently come across, also known as the Datasaurus dozen, created by Yaker and Fitzmaurice. The reference to it is there. They used mathematical model, simulated annealing, to produce 12 different arrangement of points on an XY plot, where those points are arranged in different ways. And in fact, one of the ways is looking like the head of a dinosaur. There is a wonderful little video that goes through all of those and ends up with this structure. And again, all of those data sets have the same summary statistics. And so plotting the points I think is a key way of evaluating how good a model is and how well it's performing. One thing I mentioned earlier with respect to choosing between those different statistical methods is that chance plays a big role in QSAR modeling. I describe it as the enemy of good modeling, because whenever I use a model, I say, is it better than our random selection? That, if I can prove that my model is better than random, then I know that my model is encoding some information in there, and it's not just a random chance. An interesting problem that we had quite recently is with our Witch P450 model. It is a 7-category model dealing with 7 different isoforms of cytochrome P450. And the model was there to determine which of those 7 isoforms is likely to be a major metabolizer of a compound. If you know which isoform is going to be a metabolizer, then these are the sorts of things that may bring in DDIs. It may well be something that is only metabolized by one isoform, etc. So knowing which isoforms are going to be important for the metabolism of a compound is interesting. In this, one could have thought that random chance was just going to be 1/7. But that's one way of defining random. But as scientists, we know something about this problem. We know that isoforms are not equal in their distributions. We know that they are not as influential on compounds. If one chose to pick a particular isoform and that happened to be CYP3A4, an expert would know that that is highly likely to be correct, because CYP3A4 has a large active site. It is responsible for over 50% of the metabolism of molecules that are ingested. So 1/7 doesn't describe the real random chance, and especially those where you have an educated guess, when you know something about the system. And so what we had to do with our particular model, as we've demonstrated in a paper, and we've just extracted this graph from the paper, as we were looking at our own predictions and how successful they were on the left-hand side, and comparing it with a number of different types of random. On the right-hand side, that uniform random, that 1/7 chance. The biased random, this is something where you're looking at the expert knowledge of how much a particular isoform is likely to metabolize a compound. And then a fairly standard technique of taking the data that we have and Y-scrambling it, so scrambling the real association between an isoform and a compound, and then seeing how well we could derive a model from that. And what you're seeing in this case, in all cases, that our model performed better than what you could see in random, giving us confidence that the QSAR method that we had applied was actually a worthwhile model. So dealing with random and assessing random is a key part of QSAR modeling, and there are statistics that can help you with that. Matt.
Indeed, I'm afraid we're back to the statistics, and this is a challenge that's particularly present in classification models. So here I'm showing an example of a classification model predicting human intestinal absorption, and you can see this is a very biased data set. Almost all of the observed compounds have good absorption. So this was biased towards orally available compounds, and a very small number have low. And in this scenario where we have a very biased data set, what we could see is here a very accurate model, over 92% accurate. But when you see a model for which only the accuracy is reported, that should ring some alarm bells. You want to look at that underlying distribution, because here, in fact, what you can see is it's actually a very, very poor model, because basically the model is predicting everything to be high, because in now over 90% of the cases it's correct. But that's true even for the low molecules. So the model is almost incapable of predicting a poorly absorbed compound. And so from practical purposes, it's not very useful at all. Simply randomly picking everything to be high would give you a great accuracy here, but not a very useful model. And so to correct for that, one of the statistics that we use, it's very common, is the so-called Cohen's kappa statistic, which basically corrects for the expected performance of a random model and make sure that your model is performing statistically significantly better than random. And other statistics are available, of course. Another very common one is the Matthews coefficient, but there are different ways to account for this, but be aware that just looking at the accuracy of a model can be misleading. Okay, so we've looked at different ways to assess models, different statistics, different ways to do that visually, which leads us on to another question. If I want to assess the performance of a model, what data should I use?
Well, and that data can be a problem, because what some people can do is say, oh, have you got a model that predicts this? And then we say, yes. In this case, it could be solubility. And they come back to us and say, oh, your model's not terribly good. And I said, well, actually, what solubility assay are you looking at? Here is just a particular graph of aqueous solubility versus solubility in a typical assay substitute, in an assay solvent. So you can see that there isn't really correlation between these two experimental methods for determining solubility. So when you are looking at how well a model works, it is always worthwhile really understanding what is the nature of the prediction that that model is doing. And so that can be even more complex if one's looking not between assays, but between in vitro and in vivo endpoints. We've been thinking about this in terms of mathematical and statistical modeling, but really the same principle applies if you had an experimental model, such as the permeability in cacao cells, and try and use that model to predict what you would see for human intestinal absorption here. That model does have some use, but its linear correlation is pretty limited. And we see this, and certainly from my experience in neuroscience, going that one step further, using animal models to predict human disease. There again, very difficult to know that one system is going to behave in the same way as another. So always check what it is that model is trying to predict and see whether your systems do in fact correlate. So when you do find yourself with a good model, then how do you put it to work to predicting new molecules?
Yeah, absolutely. So if we're happy with the performance of our model, the next question is, well, when or where can I actually use that model in practice? This is often described as the domain of applicability. So to what compounds can I apply a model with confidence? And this also comes to another very popular topic of local versus global models. So what do we mean by a domain of applicability? Well, as we just described earlier, a model is built using a training set of compounds. And that diversity of that training set defines the domain of applicability of the model. I've sort of illustrated that with a simple cartoon here on the right-hand side. Here, the gray points represent the compounds used to train the model in some descriptor space. So here I'm just plotting in 2 dimensions, descriptor 1, descriptor 2. Of course, we typically use many more descriptors than that, but I can't draw very high dimensional spaces. My art skills aren't good enough. And what you can see is that we've defined the domain of applicability as essentially that descriptor space that is covered well by that training set. And so if we want to make a prediction for a new compound, something like this blue star, well, that lies well within that domain of applicability. And so we can make a prediction with confidence that the model is relevant to that chemistry, and we can understand, how accurate that prediction is based on all the validation that we've done. But if I had a compound like this green star, well, that lies just outside of that domain of applicability. We're asking the model to extrapolate a little bit beyond what it's seen before. And in that sort of scenario, we would expect the applicability of the model to be lower. Perhaps the uncertainty in that prediction will be higher. And in the extreme, we might have something like this orange star way away from that chemical space. And in this sort of scenario, essentially all bets are off. The model has never seen a compound like that, and we can't expect it realistically to be able to make an accurate prediction for that particular compound. And that domain of applicability really defines the difference between a global and a local model. So a global model is trained to cover a wide range of chemical diversity. We might put as many different chemical classes into that training set for which we have data. And so it should be able to make a good prediction for a broad range of different chemistries. But there is a caveat. While it's trained to capture these sort of long-range trends across diverse chemistry, it may not pick up the impact of small changes to structure. So for example, when you're making small modifications within a chemical series. On the other hand, a local model is trained to cover a specific chemistry. It might be based only on a single chemical series or maybe a single project's chemistry. And so in that scenario, if we build and validate a good model, we would expect it to really capture that sort of higher resolution information within that chemistry. But again, in contrast, it probably won't work well for compounds outside of that chemical space on which it's been trained. So we have to recognize where we can use that model with confidence and where it simply does not apply. And Peter, I think you've got a nice example of that.
Indeed, this is a favorite one of mine from one of our tutorial data sets based on 5-HT1A activity. We have a model that was generated on one particular chemotype within this data set, and yet this data set actually contains 6 different chemotypes. On the left-hand side, we've got predicted versus actual for using a model to predict the 5-HT1A activity within this data set. And you can sort of look at it and go, well, it's not particularly wonderful. There is a bit of trend there, but really this model probably isn't all that good. But if you look at how that graph on the left-hand side is split up, if you consider each of the different chemotypes within this data set, you can see very clearly that the aryl piperazines, the series on which that model was based, is reasonably good in its ability to predict 5-HT1A activity. And yet, when it tries to predict the other chemotypes containing features which are just not there within the aryl piperazines, its predictive ability is very poor. And so this is really local does mean local. If you want to think about a model that predicts across a wide range of chemotypes, then that's how you should be creating your training set such that it covers that chemical diversity. There is a particular niche situation where you may say, oh, perhaps I will create a data set with 5 out of these 6 chemotypes and see whether the features that I've used actually extend to a new chemotype, because of course in a drug discovery project you'll usually be going into new chemical spaces to get over some problems or to get away from patent space, etc. And you need to be able to know that your model will predict in those spaces. So there are methods that you can use to really assess whether a model is good enough to predict and extend into different chemotypes, or whether you should be creating those chemotypes, generating the data, and then build a model. So the estimates on errors are a way of being able to show how much you can trust a particular model. But Matt, you've got more on errors and how to use them.
Absolutely. So looking at the domain of applicability and saying whether a compound is in or out is one approach. But actually, with more sophisticated modeling methods, we can actually generate an uncertainty or an error bar around each individual prediction. So not just saying in or out or good or bad, but giving a lot more sort of subtlety in the way we can distinguish between the quality of predictions. One example of that, and one of our favorites, is a method called Gaussian processes. This actually doesn't generate a single function, as we described earlier for QSAR models, but it actually generates a probability distribution over possible functions. I've sort of illustrated this with a little cartoon here on the right-hand side. And so you can see an example of 4 different functions here for the training set. And what we can do is, for a new compound, maybe with a descriptor value here, we can look at the spread of the predictions for those different functions. So here you can see a very broad range, and that would be the model saying, well, it's somewhere around here, but I'm not really sure. It's got a big error bar. But where all of those functions agree very closely, that would suggest a more confident prediction with a smaller error bar. So in this sort of approach, the prediction is usually reported as the mean of this distribution and the uncertainty as the standard deviation. So this Gaussian processes approach is one way of estimating the uncertainty, but other methods use a sort of an ensemble of models. They build multiple models with slightly different parameters on the data set. And just to show you an example of that, this is an example using a method called Alchemite, which is a method for deep learning, and it's employed actually by another one of our software platforms called Sorella. And this is an example of the validation of a model predicting activity, PIC50 values, in this case, against kinases. And so just to show how this estimate of the errors works, on the left-hand side, you can see here, I've plotted a graph with that root mean square error, basically the average error in prediction on the y-axis. So a more accurate model will give you a lower value here on this axis. And here I've predicted the performance on a test set. So here out on the right-hand side, if I look at 100% of that test set, you can see the root mean square error is just over 0.5 log units. And that's shown here on the right-hand side by this scatter plot. So it's got a nice correlation, but there's a fair bit of spread around that line of perfect prediction. But if I actually use the information in these error bars and I move left down this axis here, I can focus on the subset of predictions with the highest confidence. And so if I move and only look at the top 50%, the best 50% confidence, you can see here the root mean square error drops significantly. And here you can see that reflected in the scatter plot. These points are much, much closer to that line of perfect prediction. And if I move even further to the left down here and look at the 10% most confident predictions, now you see they're pretty much all nailed on to that line of perfect prediction. So you can see that when we lose the model's estimate of the uncertainty, the error bars, we can see we get higher observed accuracy. Interestingly, you will notice this one point here, highlighted in green here. This is an outlier where, you know, the model is really confident. It's got a small error bar that this is an active compound, but it was previously observed to be relatively inactive. Now, given that all of these other predictions are very, very close to the identity line, that might lead us to question the quality of this experimental data. perhaps this is an experimental error or artifact, and we should go back and retest that because it could be a valuable active compound that we might otherwise have missed. So we've talked a lot about uncertainty. And so I guess in the face of all of that uncertainty, how do I know if my model is actually good enough for the purposes of my drug discovery project? Peter.
That to me is a question that's really the QSAR equivalent of how long is a piece of string. In all of the questions of how is it good enough, I would ask, what do you want to use that model for? What's the purpose of it? And just to illustrate here, I've got two models here, model A and model B, and they are models that I've created for a fire engine. Well, if my purpose for a model is to recognize a fire engine when I'm driving along the road and basically be able to get out of its way, then model A here is going to work. That will give me all the information I need to know to recognize a fire engine. However, if the purpose of my fire engine model is to put out the fire that happens to be raging in my waste bin, then model B is the one that I would go for. And so a model is usually fit for a purpose, but that purpose may not be the one that you originally intended it to do. And so if I go back to that in vitro model for an in vivo activity, the use of the CACO2 permeability assay here to predict what is going to happen in human intestinal absorption, well, as we said, the linear relationship is not particularly good. But if one took that model and so it said, right, well, if I have a CACO value that is above about 1.5 here, then I'm going to be very certain that that compound is going to have a good human intestinal absorption. The model is not perfect. It doesn't have any false negatives here, false positives, I should say, but it does have some false negatives. So it's missed a few compounds, but the model using this CACO assay, if I look for a particular value, I know that it's going to be useful in identifying some good compounds and eliminating a lot of the poor compounds. Also, as we've been describing, uncertainties and errors are really things that need to be paid attention to, not only when you are assessing a model, but assessing the output of that model. Here we've got a set of compounds. We just ordered them by their activities. This is just made up example of PIC50s here. And each of these predictions has a very small error bar. Therefore, you know that because you've got these small uncertainties, that you're able to rank order these compounds and distinguish one compound from one further on down, because the accuracies of these predictions, the uncertainties in these predictions are small. However, take exactly the same data, the exactly same set of predictions, and yet this time the model has inherently large uncertainties. You can see these error bars on these points are very large. And therefore, yes, you can rank order compounds, but the utility of this model is only to separate the good from the bad, because it's at that point that you really are distinguishing and able to distinguish that something is likely to be good versus something which is likely to be bad. All of the middle compounds here, you really don't have enough information, or it's not accurate enough to be able to make the correct decisions. And so you should use that model with that in mind. And so it's not only the use of predicted data, but if you were thinking about this particular graph here for experimental data, it is unreasonable to think that that data will produce a good model for you, because that data is highly uncertain, and therefore the use of that data can only provide you with a model that will distinguish good from bad. It will not provide you with information enough to rank order compounds with any confidence. And again, we've got a made-up example here which has 5 orders of magnitude. If this was an axis that only dealt with 2 orders of magnitude, and you had the same error spread, again, expecting that data to be able to generate a model that can be useful over a large range is unrealistic. And so always think about the quality of the data that you have when you put into the model, and the uncertainties in the predictions as to what it is that you can use that model for. And so, given this comments about uncertainty, Matt, you have a few more comments about that.
Indeed. I guess we've been talking a lot about uncertainties and imperfections in models, which might seem a little bit depressing. So let's say, well, given all of these uncertainties, how can I actually use them in practice? So when we're making a decision, we'd like to choose between compounds. So here I've got some property Z or Z, depending on which side of the Atlantic you're on. And I might have some criteria. Maybe I've got a desirable range, active compounds, and an undesirable range where the compounds are not sufficiently active. And if I had this decision to make, then on the right-hand side, these are the compounds we would choose to take forward, of course, and the ones on the left-hand side we would reject. So let's imagine I have predictions for 3 different compounds. Let's call them A, B, and C, and I want to choose between these compounds. Well, clearly A and B are the wrong side of this criterion here, and C is to the correct side. And so I might be tempted to say, great, let's just reject A and B and take C forward. But of course, it won't surprise you that we're only looking at half the information here. We should also be looking at the uncertainties in these predictions. So if I illustrate those as a probability distribution, this little bell curve here, you can see the prediction for A has a degree of uncertainty, but the chance of that actually exceeding that threshold and being good enough is very, very small indeed. On the other hand, if I look at compound B, it's quite close to that criterion, and given that uncertainty, you can see the shaded region is the probability that it will actually meet our activity requirements. So, yeah, we've got a reasonable chance of success here. And if I look at compound C, it looks to be my best. It's the correct side of that threshold, but actually, there's a significant probability, again, this shaded region here, that it actually is not good enough. So in this scenario, my conclusion really should be reject compound A with confidence. Great, we can save that time and effort. But B and C are in a sort of a gray region here where we cannot yet confidently choose between them. We would need to get some more accurate data, maybe send it off and get it tested in practice. Or if we're dealing with multiple replicates, we could measure it multiple times and get a more accurate estimate of the activity of those compounds. And it's even more complicated. Again, here's my threshold that I had before, and maybe I've got 2 new compounds, D and E. Both are the wrong side of that threshold. They're undesirable. But maybe those are my 2 best compounds. It's either pick one of those or forget about it, really. And so again, here we might be tempted to say, well, compound E is closer. That's great. Let's take that one forward. But again, if we look at a bit more information, what we discover is that the uncertainty around that value for compound E is very, very small. That's a very tight probability distribution. And hence that little tiny area shaded there is the probability that it meets our requirement. Whereas for compound D, actually, we've got a lot more uncertainty. In fact, the probability there of it meeting our requirement is actually higher, even though the best estimate is further away. So in that scenario, I would argue that compound D has a higher chance of success. That's where I would focus my time and effort. And of course, the first thing I would do is get some better data on compound D and really determine where it lies relative to that threshold with higher confidence. So we can take this uncertainty into account when we're thinking about these decisions and these choices that we're making. Now here I've illustrated a very simple example where we've got a sort of a hard cutoff, a hard threshold here. We've got good and bad. Of course, real life isn't that simple. We saw an example of that in the data that Peter shared in terms of CaCO2 permeation. So here's that graph that Peter showed before of the human intestinal absorption versus CaCO2. And we might say, well, if I have a high CaCO2 permeability, as Peter described, then I'm really sure that this has got good absorption. But for low CaCO2 values, essentially all bets are off. So we can ask another question, which is, well, for a given value of the CaCO2 permeability, what's the chance of a compound achieving a human intestinal absorption of greater than 50%? And we can look at that as a histogram here. So here's my CaCO2 permeability. Here's my proportion meeting that criterion. And so again, what you can see is for high values, yep, I'm sure that's going to give me a good human intestinal absorption. But for low values, again, doesn't necessarily mean that it's a bad compound, but it's got a lower chance of success. And I could represent that as a sort of a mathematical function here. This is commonly described as a desirability function that relates the outcome of an experiment to how desirable that is in terms of my ultimate goal. So again, that's a lot to think about. You don't want to be thinking about all of these for each individual parameter in which I'm interested. And so this is where the concept of multi-parameter optimization can really be very, very powerful. And in particular, we have a method in our Stardrop software called probabilistic scoring that enables you to define your requirements for a range of different properties. And again, this could be experimental data or predictions from a model. You can say, what am I looking to achieve? And also, what is the importance of each of those? Because some properties are critical. I must have a potent compound, but other properties we might be willing to compromise or trade off to do better in those critical factors. And in fact, underlying each of these can be one of these desirability functions as well to give you that sort of more subtle trade-off. And what we can do using this probabilistic scoring approach is automatically bring together our property data, experimental or predicted, assess them against our criteria for success and their relative importance, but take into account the uncertainties in that data. Again, the experimental variability or statistical uncertainty that Peter spoke about. And we can calculate a score that represents the chance of success against all of our criteria, all of these requirements for a high quality compound. And we can bring together all of these different sources of uncertainty in our data to calculate a confidence. And this enables us to more rigorously rank order our compounds. Here I'm showing them ordered from the best on the left to the worst on the right. And we can look at the confidence in the overall score as well. So given the uncertainties in the data, what resolution does that give us in our ability to choose between compounds? So here, for example, you can see this overall score on the y-axis. Our best compounds have about an 80% chance of success, which is great. But you can also see that for these top 5 compounds, the error bars overlap almost completely. And what that means is that the data we have so far, the predictions or experimental data, do not confidently distinguish between those compounds. If I tell you to go after compound 1, you're going to go, wait a minute, hang on. We need some better data with smaller error bars or another criterion with which to choose between these compounds. Whereas you can see for roughly the bottom 50%, you see the error bars don't overlap. And we can say with confidence, these are very unlikely to be as good as our best compounds. we can reject those and save our time and effort and really focus here at the top end of the scale, maybe getting some more data or exploring that chemistry further. So we can bring together all of this uncertainty without having to look at every single distribution and error bar, which would be a very tedious and time-consuming process. So that's a little bit about how we can use this sort of uncertain information to choose between compounds for our projects. The next question is, well, can I actually use this information to design new compounds? And over to you again, Peter.
Thank you very much. And so we're moving really now from the general ranking to looking at specific molecules and how the QSAR models can help you with those specific molecules. Matt introduced probabilistic scoring for you, and this is what it would look like within StarDrop. You see the snake plot, the ranking of those compounds, and you can see a couple of compounds here represented in card view. They have the same chance and probability of success, but the things that need to be improved with these compounds are different. One on the left, log S and log P, are less than desirable, but on the right hand side, we're back to again our favorite 5-HT1A data. It's the activity which is not meeting the required value. And so when it comes to interpreting a model and using it to design new compounds, it really is the description of a molecule, the features that you consider to be important or are likely to be important and influential on a particular endpoint. That is the key to getting successful QSARs. And descriptors really need to be relevant to the property being predicted. So log P is a really good descriptor in lots and lots of cases, but I would say that it's not likely to contribute to any individual atoms pKa within a molecule. I also like to think and look at descriptors with the view of interpretability. I don't like black boxes. Yes, they are useful in terms of QSARs to evaluate lots of compounds, to rank those compounds, but if you're thinking about how do I modify my compound to get the sort of desirable property that I want, then the descriptors that you've used, those X values in the equation that we showed at the beginning, they really have to be interpretable. In my particular bugbears like E state and B cut descriptors, I have no idea how to change a molecule to change those descriptors. And so what you want to have is the ability to take a particular structure, describe it in a way that you can then take the influence of that structure, mathematically relate it to your target endpoint, and then be able to feed that influence back. And so what we have within StarDrop is what we call the glowing molecule. Really, it is a way of getting that atom to atom topology, the relationship between the structures, and mathematically knowing how that topology relates to the target endpoint. And when you know that relationship, you can feed that back and map it back onto the structure to be able to say, this area of the structure is giving you a desirable property, or this area is responsible for undesirable. In our case, we use the colors red and blue to indicate which areas of the molecule increase numerically a particular property or decrease numerically a particular property, because we don't know what you consider good or bad, desirable or undesirable. You could be looking at a primary target, or you could be looking at a counter target, in which case you want to be looking at removing activity and therefore a lot more blue areas in a molecule. But looking at something like the glowing molecule here gives you that direct impact of what changes you make to a molecule to see where in fact you have improved or not improved a particular prediction. And if you're coming afresh to a new lead, it gives you the indications as to where you should be considering making changes to improve the properties that you want to improve. And so with this, I hope we have covered a lot of the common questions and concepts with QSAR modeling. Matt, do you have anything else you would like to add?
I will just mention the fact that we've talked a lot about building and applying models in our software, in our Stardrop software. On the left-hand side here, we have a module that Peter's referred to called the Auto Modeler, which really embodies all of the different approaches that we've spoken about today and the sort of the key sort of features and philosophies that we've really described. And on the right-hand side, you can see here our Sorella software, which really goes beyond QSAR using a really unique method called deep learning imputation, but still in that very statistically rigorous ways that we've really spoken about here today. So a really great question here. What are some methods you like to choose relevant descriptors? Peter, maybe you could take that one.
Yeah, I mean, again, I suppose the thought process for me is, what do I want to do with that model? If I just want to do ranking, then I tend to think about the topology of a compound. My history is with Merck, so atom pairs, topological torsions were descriptors that were really useful in capturing the relationships between a structure and its influence on its environment. So my default is to go to those type of descriptors. But if you're getting to large numbers of descriptors, then I would even think about doing principal components analysis on that descriptor matrix to start with, to get down to a smaller number of descriptors, and therefore really increase the information content that's there. And I tend to not have a lot of descriptors because that just increases your chance of chance correlations. But I would be, starting with the interpretable descriptors, and then if I don't get a model, then I'd be rethinking and really looking at what are the processes that are likely to be involved in whatever endpoint I'm modeling, and try and think of ways of expressing that and describing that in a molecule. So no particular software, just really thinking about it ahead of time.
Certainly that sort of pre-analysis of descriptors can be really helpful to make sure you're including ones that are relevant to the process, the mechanism that you're trying to model. It should be said that many modern machine learning methods do include the ability to calculate the importance or relevance of individual descriptors. So you can actually include large numbers with some of these methods, things like Gaussian processes or the Alchemite method that I mentioned, and it will look automatically for those descriptors that have the strongest correlation. And for many of the descriptors that have no strong relationship with the observed property, they will have no impact on that prediction. So it avoids overtraining in the way that Peter described. And in some cases, it can be useful to include a broader range of descriptors because they can also capture more information about that domain of applicability or the confidence in the prediction. If a descriptor that has been found to be unimportant is included in the descriptor set used for the model, then if you start to see values that differ very significantly from the training set, your assessment of the importance of that descriptor is no longer valid. And so therefore your uncertainty should go up. Maybe it does have an impact for these very different compounds. So there's a different schools of thought here. And that sort of importance calculation or automatic relevant determination can be very, very powerful indeed. Here's another great question. For local models, I might extend this to say for any model indeed, is there a rule of thumb for determining what is the minimum number of data points that you should have before trying to build a model? Peter, do you want to take that one as well?
Yes, it's again, I suppose, another one of those how long is a piece of string. We normally think about any regression model that you need 5 data points to think about, even having 4 to build a model and 1 to test it. But really, there is no rule as far as I'm concerned, because as I described within the talk, you could have 100 molecules, but if 90 of them are inactive and 10 of them are active, then you've got a highly biased data set, and you'd have to be very wary about the model that you're creating. If you happen to have a data set with 2 chemotypes, one of them being poorly active, one of them being active, again, there's a bias within that data set which makes modeling of it difficult, or at least interpretation of the model afterwards difficult. So no, unfortunately, there is no easy way of saying these are the minimum number you need. But if you're looking at a particular property, then think about the dynamic range of that property, and do you have compounds, representatives within your training set that cover that dynamic range. If you're thinking about the global versus local, again, if you want a global model, then you're looking at a large number of compounds, or larger number of compounds, just to have enough chemical diversity to be able to bring those features into play and make that model global rather than local.
Yeah, I think that's really important. The globality, or the diversity of the chemistry that you're trying to predict is really important. The other thing to bear in mind is the complexity of the property you're trying to model. So if you're looking to predict something relatively simple, say, binding to a relatively simple sort of binding site on a target, you would typically expect to need fewer compounds than trying to predict something that is highly multi-mechanistic, something like microsomal stability, where there are many different factors that can influence that experimental measurement. There, to really dissect those different mechanisms for different chemistries and different compounds, you would need to have much, much more data to be able to capture that signal. And so it can be a huge range. At the low end, just to give you some rule of thumb or guidelines, for a very simple model for relatively local chemistry, high numbers of tens of compounds, 50 to 100, can be sufficient. I guess we'd be more comfortable typically with over 100. But at trying to build a global model of a very complex property like microsomal stability, I've seen published models with tens of thousands of data points, where when I look at the statistics, I don't think it's a model that I would use in practice. And so, there it may almost be impossible to get enough data to really dissect that complex property.
In addition to that, though, Matt, I mean, some of our modeling that underlying the metabolism, we're using the DFT descriptions of that transition state and be able to sort of use that methodology on very small number of cases, but at least we have a range of the experimental data that we can correlate our energetics with, to be able to have confidence that our modeling of that system is accurate. And so in this particular case, when you have a small data set, then you could use quite intense and intricate descriptions of molecules, as long as you have the ability to cover the dynamic range that you're thinking of in the property that you're thinking of.
Yes, that's absolutely the case. And yes, in the case of our metabolism models, there we're using that highly mechanistic description. So there's a lot of information in that descriptor, the activation energies of the energetics of that reaction. So there, again, where you have something that is really information rich, you would typically need fewer descriptors. You're absolutely right. Well, I'm aware that I'm certainly enjoying this conversation a lot, but we are running a little bit late. I'm going to throw one more question in there, but we had one question here which actually relates to a topic we've discussed, which is bias in a data set. So if you're to build a binary classification model using known, carefully curated actives and inactives, how many would you think to be the lowest you can go in terms of the known actives versus inactives, that bias in the data set? And I might start with this one and pass over to you, Peter. So a bias when building classification models particularly is a real challenge. You could imagine a data set where 99% of compounds are inactive and 1% are active. Well, the default model of predicting everything to be inactive is going to be 99% accurate. So it's very difficult for the model to find a signal to really distinguish those active from inactive compounds. And this is true of many methods, random forest, recursive partitioning, and so on. They really aren't very good at those situations. So typically you would want to have a significantly higher proportion of compounds that are active, or higher than 1% anyway, in order to have a chance of building a good model and pick up that signal. There is one sort of exception to that I will mention, which is in our MPO Explorer module in Stardrop, we actually have another method called the patient rule induction method. And that is actually specifically designed to deal with these highly biased cases. The patient rule induction method was developed by Friedman and Fisher, who were the inventors of decision trees or recursive partitioning, specifically to address this question. And if you're interested in that, you'll find lots of examples and publications on our website. But Peter, I'm sure you have some examples of how to treat these highly biased cases.
In my case, I would be thinking very much in terms of the consensus modeling. And again, what it is that I'm trying to get from the model that I'm producing. And if we're thinking about the classification side, then obviously your large number of inactives, should we say, describe what it takes to be inactive. They are looking at a particular set of chemical space and saying this area seems to be dealing with inactivity. If you have a biased set like that, one would think about trying to make it unbiased by having the same set of active molecules and a roughly equivalent set of inactives, thereby taking away that sort of bias within the set. But by doing that, you're likely to be missing information. And so I tend to think about doing several splits of a data set where I have splits of the larger inactive set, but all of the active set. And then those individual models that I create will have predictions, and I will use the predictions from those models in a consensus form to be able to say how well do those models predict a new compound. So I'm trying to get rid of that bias, but in doing so, I come up with more models to try and hopefully encounter and encompass all of the information that is contained within my data set. So that would be the technique that I would use. Again, it really depends upon the size of your smaller set. One other thing that one could do, I suppose, is move the boundaries. If you happen to have a particular continuous scale that you've said over this is active, under this is inactive, well, try shifting that particular boundary. See whether you can change the bias within your data set. Do you produce better quality models that can at least get rid of confidently inactive molecules? And then you can start thinking about those that you've predicted to be active or potentially active and doing some more analysis on those. So those would be my techniques.
So at this point, I am going to wrap up. again by saying a big thank you to you all. Just a reminder that if you do want more information, please feel free to contact us at info@optibrium.com. So thank you all, and we look forward to seeing you hopefully at another webinar soon.